I'll be explaining part 1, stepper motor controller. So we were given 3 requirements. The first requirement is EN, enable stepping. Second is control the direction of stepping, CW. And the third one is the clock. So when EN is 0, the output will remain fixed. When EN is 1, the output will change from one state to another state. When CW is 1, it will be clockwise. When CW is 0, it is anti-clockwise. So from these requirements, we're able to build a state diagram here. When CW is 1, it is clockwise. So when CW is anti-clockwise, when CW is 0, it will be anti-clockwise. When EN is 0, it will remain fixed, remain the state. So when EN is 1, it will change state. So from this state diagram and the flip-flop excitation table, we were able to build this table here. So from this input, from JB, KB, JA, KA, we're able to build this K-map expression. So the input for JA and KA is EN, while JB and KB is EN, CW, and A. The output functions here is from this table here. So output 0 is 1 when A and B is 0. Output 1 is 1 when B is 1 and A is 0. Output 2 is 1 when B is 0, A is 1. Output 3 is 1 when A and B are 1. So from these 8 expressions here, we're able to form our schematic diagram, where 74HC107, 74HC108, 74HC00, and 74HC02 are used. These are the connections that are constructed, where 200 kHz are used in here. And this is EN switch, and this is CW switch. So when EN is 1 and CW is 0, it will move in anti-clockwise directions. So when CW is 1, it will move in clockwise directions. If EN is 0, it will remain fixed, no matter CW is 0 or 1.
Hi, my name is Lucas. I'll be explaining on level 4 state machine designs and explaining on the part 2 linear feedback shift register. Right here we have our circuit here, we built it. We have a 74HC164 shift register and a 74HC86, which is the XOR gate. And now we built this according to the schematics here. And so right now you can see it has no output. So what we have to do is that we have to force this to be a 1 in order for the output to go. So it goes like this. Okay, so now you have an output. So according to this, right, it should be like 100 to 010 to 101. So how we get a 100 is from the initial one. Our x0 is 0, x1 is 0, x2 is 0, and then we get this 100. So according to this schematics here, our D0 is equal to the x1, which we will get a D0 is equal to x1 is 0, D1 is equal to x2, D1 is equal to the x2, which is 1, and D3 is equal to the XOR of x and x1 and x0. So x1 is 0, x0 is 0, you will get a 0 D3. And for the oscilloscope here, will be our x0. So according to this, when it is high here, the clock is high, and you see this. Next, when it's high again here, it will go down, right? High again here, it will go down. So the next one, it will go up again, the clock is here, up, it's high up here, right? So the next one, and like around here, it will, when the clock is high, it will go down. So you can see that the sequence here is not pseudo-random because it's the same here all the time. It will be on. On the second part, the part B here, we're talking about the 7-bit LFSR. We modify our circuit, based on this thing here. So we will have our schematics. Previously, when on the pin 1 of the XOR gate, we are connected it to the X1. Okay. And this X7 here, the pin 6, previously it is X3, so we change it to the X7. After modifying our circuit, this is what we have as our output. And setting our input as a 500 kilohertz, this is what we get. So you can set it appears as a pseudo-random. That's all.
We'll be doing lab 4, part 3. We will be designing a mini state machine to detect the sequence 0, 1, 1. First, we will come up with a state diagram where you have 3 states here, which is idle, F0 and F01. So when the output is, when the machine is at idle and the input is at 0, there will be no output. If it's F0 and the input is 1, there is still no output. But if it's 1, 1 and it's F01, then there will be an output and it will go back to idle. This thing here represents if it's the state idle, and if it's 1, it will still be no output. And if it's F0 state and the input is 1, there will be no output. And if it's F01 and the input is 0, there will still be no output and you'll go back to F0. From this state diagram, we will come up with this state machine table. Here you will see that if it's when W is 1, then there will be an output. And from this, we derive the K-map. And from the K-map, we come up with the Boolean algebra expression from here. And from this K-map, we will design our circuit as shown here. VW represents the AND gate here, which is 74HC08. W0 here will represent the NAND gate, and AW will represent the AND gate here. So in our oscilloscope, we have 2 channels, which is channel 1 and channel 2. Channel 1 is W, and channel 2 is F. We want to look at our circuit here. We have our NAND gate here, 74HC00. Our D flip-flop here, 74HC74. Our AND gate here, 74HC08, and our shift register, 74HC164, and our XOR gate here, 74HC86. If you look at our output here, when W is 0, 1, 1, then we have an output here 1. 0, 1, 1, and we have an output here 1. That's all.